Now, the first example we can think of is this number one, horizontal circular motion of an object. I'm emphasizing the word horizontal. Horizontal circular motion of an object connected to if it is a inextensible string, horizontal circular motion of an object connected to an inextensible string. Inextensible means you cannot apply Hooke's law. So length is constant. Length of the string is constant. Length is constant. It's like a rope. You can think of a rope. So that is pretty straightforward. Now, since it is horizontal circular motion, I'll go with horizontal table or something like that. If not, if I draw the plane wave, it might be confusing. So let's go with the 3D structure. Imagine there's a table like this, and on the table we are allowing an object to perform circular motion. Let's say this table is smooth. Okay, let's not include what you call that friction also. So the object is performing circular motion on the table like this. And what is going to be the centripetal force, people? What is going to be the centripetal force? The object is connected to a string like this, and the object is performing a circular motion like this on the table, right? So I'm seeing it from the side. That's why it looks like this. You get the picture, right? You get the idea, right? The object is rotating like this, and the object is fixed here, and it's rotating like this on the table. And how many forces will be acting on the object, people? Just like we discussed before, there will be two forces. One will be weight, which is the vertical force, and the other force will be tension, which will be acting towards the center. And let's say the length of the string is L. Length of the string is L. Length of the string is equal to L. So whenever object is performing circular motion, we have to define two things. That is, one is the the tangential force, and the other one is the tangential acceleration. Tangential acceleration. The other one, tangential velocity, and the other one is the angular velocity. Now I have missed another force. There will be a perpendicular reaction acting on the object as well. Yes, but the perpendicular reaction or weight will not influence the centripetal force, because we need a horizontal centripetal force. Horizontal. So if the circular motion is horizontal, we need to go for horizontal force. So these two are vertical forces, therefore horizontal force. Right, fine. Now for this case, what is the centripetal force, people? For this case, what is the centripetal force? Centripetal force is equal to, without much of deliberation, yeah, it should be tension. Centripetal force is equal to tension. So they will provide you the value of the tension. Then for centripetal force, you can apply the equation. Instead of centripetal force, you can put mv squared over L. Why? Because radius of circular path is actually the length of the string. Radius of circular path is the length. Circular path is equal to the length of the string. Okay, so mv squared over L is equal to T. I will stop it here. Now I don't know. We don't know what they will ask at the in the questions. When we do questions, I don't know what they are going to ask. But to be on the safe side, for T, I will use F force, just as a tension. So I'm using F for T, yeah, because in some questions they use period of rotation as T. So there we might get confused. So to be on the safe side, I'll use F for tension, F, because it's a force. Then that way we are safe. F is F is tension. Right. Now I'll stop it here. In different questions, they will ask you to find different things. Sometimes they will ask you to find the speed. Sometimes they will ask you to find the force. Sometimes they will ask you to find the length. We don't know. So I will leave it here. After that, you will manipulate the equation according to the requirement. And then another one, centripetal force acting on the object is the tension. And instead of centripetal force, I can use another equation. What is that? That is ml omega square. If not, wait. To be more clear, let's substitute mv squared over r, but we know r is equal to the length of the string. Therefore, mv squared over L is equal to the tension. And here, instead of centripetal force, we can use mr omega squared equal to F. But again, the radius of the circular path is the length of the string. So ml omega squared is equal to F. These are the two equations you can develop. These are two equations you can develop. And one more thing, sometimes people, they might ask you, they might develop this equation further. But for omega, we learned an equation last week. What is that? 2 pi divided by capital T. Correct? And T is period of rotation. T is period of rotation. Okay, so sometimes we might have to substitute that here. Then what will happen to the equation? ml into 4 pi squared over T squared equals F. Why? Omega squared. If omega is 2 pi over capital T, omega squared is 4 pi squared over capital T squared. Now, this is the first question we are going to try based on the horizontal circular motion of an object connected to a inextensible string. So what does the question say? Masses capital M and simple m are connected by an inextensible light string, and mass simple m is allowed to perform circular motion on a horizontal smooth table. So you can see simple m is the one who is performing the circular motion. Right. So simple m, if it is performing circular motion, it will have an omega as well as a tangential speed like this. And more importantly, the force acting on the mass is going to be the tension. We'll take it as T. And the same tension will be acting here as well. So let's read, while exactly half of the string on the table, M is at rest while simple M. So capital M is at rest while simple M is rotating. Therefore, on capital M, there will be two forces, mg and capital T. Okay. If this is at rest, so what can we say? So T must be equal to capital Mg. Find the angular velocity of simple m. Length of the string is L. Therefore, if the length of the string is L, only half of the string is on the table. Therefore, I can mark the radius of the circular path as L by 2. This is R, and that is going to be equal to L by 2. Why? This is half of the length of the string. Half of the length of the string, and that is going to be L by 2. Okay, R is equal to L divided by 2. Fine. So if all set, and we are supposed to find angular velocity. When they say angular velocity, we have to find out actually omega. So if you want to find out omega, the approach is going to be this equation: centripetal force equals mr omega squared. That is what we need to find out. Now we are applying the equation for simple m, because that is the object which is performing the circular motion. Now, what is the centripetal force acting on simple m? There is only one horizontal force acting on simple m, that is tension, T, equals m. Instead of radius, you have to put L by 2 into omega square. But since capital M is also connected to simple m, tension is equal to capital Mg, because this is at rest. So instead of capital T, you can substitute capital Mg. That is equal to ml by 2 omega square. Now we are supposed to find out omega square. Therefore, I'll take this to the other side, this to this side. Then I'll end up in 2mg over ml, that is equal to omega squared. So finally, omega is going to be equal to square root of 2mg divided by ml. This is the answer. In case if you come across a question like this, is not a past paper question, this is just a model paper question. Right. Well, let's move on to a past paper question now. It's from year 2004 MCQ. Let's see what it says. Two small objects of equal masses are attached to each other by a light string BC. And this system is connected to a fixed point A with, with another light string AB as shown in the figure. Now, if you're confused where the objects are, this is one object. This is another object. I think those objects are not properly visible. And they both have equal mass. Therefore, I'll put M here and put M here. Okay, M and M. And since this tension, it's a bit dark, bigger, they are marked it bigger, so I'll just wait. The tension T2, which is supposed to act here and here, so I'll erase it and mark it small. Here T1 is the tension acting on string BC. Let's mark it properly so that it's clearly visible. So there will be a T1 acting here, there will be a T1 acting here, there will be a T2 acting here, right? And there will be a T2 acting here as well. Right. So the radius of the smaller circle is r, the radius of the larger circle is 2r. Masses are then made to move in horizontal circular paths of radii r and r2, r and 2r with the same angular speed. With the same angular speed. So both the objects have the same angular speed. This m, it has omega, and this also has omega. They both have same angular speed. Right. So that points A, B, C are always in a straight line. Yeah, if they both have same angular speed, what will happen? When this mass performs one rotation, this mass will also perform one rotation. So they will be in one straight line. If T1 and T2 are the tensions of strings BC and AB respectively, then we need to find out the ratio between T1 and T2. That is going to be your task. In this question, the things we need to consider. Now there are two masses, one is at B, one is at C. And the masses are equal according to the question, equal masses. Therefore, I have marked their masses as M and N. And for the mass at B, the radius is R. For the mass at C, the radius is 2R. Now, what you need to do is just the basics, Let's start with mass at B. For mass at B, let's apply the equation centripetal force equal to mr omega square. I have to use mr omega square because they have mentioned about omega. They both have same angular speed. Fine. So mass B, you have to be very careful. What is the centripetal force acting on mass B? Centripetal force means resultant force towards the center. Resultant force towards the center, and that will be T2 minus T1. Because you see, there's a T2 acting towards the center, there is a T1 acting away from the center. So the resultant is T1 minus T2. That is equal to M multiplied by the radius of that mass at B is R, and omega will take it as omega square. So the equation is T2 minus T1 equals mr omega square. Let's take it as equation 1. And then you apply the equation for the mass at C. When you apply the equation mass at C, again, the main equation is centripetal force equals mr omega square. Now, what is the centripetal force acting on this mass? There's only one force acting on that mass. Okay, this is acting on beam, so the only one force acting on that is T1. That's all, nothing else, just T1. T1, that is going to be equal to M into, now you have to be careful, for object at C, radius is 2R. It is in the outer circle, so you have to put 2R here. 2R into omega square, and finally T1 is going to be equal to 2mr omega square. 2mr omega square. We need to find out the relationship between T2 and T1. Right, I have T1. Then if I go to the first equation, what will I be getting? T2 minus, instead of T1, I can substitute this value. That is 2mr omega square equals, on the right side I have mr omega square. Therefore, T2, it's equal to, this 2mr omega square goes to the other side. It becomes 3mr omega square. Right, then let's, this is equation 2 and this is equation 3. Let's divide 3 by 2. When you divide 3 by 2, you will be getting T2 divided by T1. T2 divided by T1 equal to, on the right side, what are we going to get? 3mr omega square divided by 2mr omega square, and that's going to be 3 over 2. And ultimately, we need to get an answer for T2. If I make that the subject, T2 is going to be equal to 3 over 2 T1. And that is the fourth answer. That is the fourth answer. So the most common mistakes people make in this question is, most common equation in this equation they make in this question is this part. For B, you might have missed to mark T2 minus T1 for the centripetal force. T2 minus T1 for the centripetal force. So that's the major mistake you people might have made. Instead of T2 minus T1, you might have substituted T2 here, and you must have substituted just T1 here. So that is one of the major mistakes you might have made. So careful, you have to put the resultant force. The next question is from year 2005. What let's say, a sphere, capital M, attached to a thread. Is whirled in a horizontal circle at a constant speed as shown in the figure. The forces acting on the sphere observed by a person who is who is a person who is at rest laboratory, best represented by, okay, how many forces are actually acting? How many forces are acting? The weight will be acting, okay, the weight will be acting downwards, and the tension will be acting like this. That's all. You cannot mark the centripetal force as an extra force. So what one thing you can do is you can take this as theta. Therefore, you can say now this is tension, right? So you can say this also is this will also be theta, right? So that's a tension acting. You can take the component of theta, then t cos theta here, and then t sine theta here. T sine theta and t cos theta, they are not additional forces. They are the components of the existing force. So there's only going to be two forces. One is the tension, one is the weight. Therefore, answer must be second. Now, this indicates that there is a third force. Now, it is not an additional force, unfortunately. So, you have assumed that this is centripetal force, but it is centripetal force. It is not a new force. It is the component of this. Therefore, we don't mark that. The force is acting on the sphere, observed by a person. Forces acting on the sphere. That is what you have to focus on. So, you should not mark the centripetal force as an additional force. Second is the answer. Now, this is a similar question from year 2001. Again, they're asking for the forces acting on the object, right? Let's see. An object moves along a horizontal circular path on a inner surface of a smooth conical shaped vessel, as shown in the figure. The force or forces acting on the object as observed by a stationary observer is R. Right. So, what are the actual forces acting on the object? There will be the weight. I'll draw the object here, somewhere here. Okay. There will be the weight acting on the object, and since the object is in contact with the surface, there will be a perpendicular reaction acting like this, perpendicular to the surface. And weight will be vertically down. If it is confusing to you, I should draw vertically down the weight like this, right? Vertically down, whereas R must be drawn perpendicular to the surface like this. So these are the only two forces which are going to be acting on the object. So yeah, second one, weight of the object and normal force, reaction force normal to the surface only. I think there must be a printing error. One of second and third must be different. My point is, yeah. Now, centripetal force. Now, what is the centripetal force for this case? What is centripetal force for this case? It is not an additional force. It is going to be the component of this R. It is going to be the horizontal component of this R. This is theta. Then R cos theta is going to be the centripetal force. So that is not an additional force. That is the component of the already existing regular forces. The answer for this is second. Right now, the next case is going to be about extensible strings, where we can apply Hooke's law, horizontal circular motion. Right, fine. So let me analyze it very quickly. Now, imagine there is a spring fixed to a point and connected to an object like this. And initially, there is no, what do you call that, tension. No tension. And its length, I'll take the length as L naught, the initial length. I'm just using the symbols. L naught is the initial length, where there is no tension acting. L naught, object at rest. Object is at rest. So tension on the spring is equal to 0. Extension is also 0. No tension, no extension, because F is equal to Kx. Right. Now, if you make that object rotate in a circular path, that means you throw it on a horizontal table, then what will the object do now? It will perform a circular motion. When it performs a circular motion, the spring will get slightly elongated. Why is that? The spring will get slightly elongated. I mean, why is that? Because there must be a tension acting on the object for the circular motion to be taking place. Okay, for the circular motion to be taking place. Therefore, the spring will get slightly elongated to create the tension. Spring will get slightly elongated to create the tension. Therefore, now there will be a tension in the spring. I'll take it as T. What would have changed? The length is now different. L is the new length. L will be the new length because it's performing circular motion. So if it is performing circular motion, it's going to have an omega, and also it's going to have a what do you call that? Tangential speed as well, like this. Tangential speed and omega. Okay. Now this L is something else as well. What is this L? This L is something else as well. What is that, please? What is this L going to be? It is something else as well. What is it? Good. This L is going to be the radius of the circular path. Very good, right? L is going to be the radius of the circular path, because now the total length of the spring must be considered as the radius of the path. Right. Now, after that, more or less everything is same except for one small step, that is finding this T, tension. Okay, we need to find that tension using Hooke's law. Now, let's say they have given the spring constant as K. Okay, K is the spring constant of this spring. Now, can you first of all tell me what is the extension in the spring? Extension equal to X, and X is equal to, can I get some very quick answers, please? What will be the extension on the spring? Easy. What is going to be the extension? Good. One correct answer so far. How about the others? Now the new length is L. Initial length is L naught. Therefore, the extension has to be L minus L naught. That has to be the extension. Right now, if you apply Hooke's law, we know F is equal to Kx. What is the force acting on the string? That is, or spring, that is T, the tension, and K into the extension, that is L minus L naught. L minus L naught. Okay, right. So that is ready. That is ready. That's the tension. Now let's go to the equation. Let's go to the equation. Centripetal force is equal to mv squared over r. That is one path. Or else, depending on the question, you can go for the other equation as well. FCP is equal to mr omega squared 2. Now, what is this? The centripetal force here acting on there's only one horizontal force, that is the tension, T, equals mv squared over, for r, you have to carefully substitute L, the length. And instead of T, but we know for capital T, we have derived an equation, that is K L minus L naught. L minus L naught. So, if we substitute the value there, it will be K bracket L minus L naught equals mv squared divided by L. Now in the question, it depends on the question. They will probably ask you for the value of V. Then I'll just make it the subject for the time being. V square is equal to KL L minus L naught divided by simple M. And if they ask for V, then what will you do? You will take the square root and say KL L minus L naught divided by simple M. Now you don't have to by heart this. Even I can't remember this. Whenever you get a question, you just have to start from scratch quickly. You will supply the equations and get this answer. That is how it happens. Okay. Now they might not necessarily give this as L naught, this as L. They might give the extension as X or L even. I don't know. It depends on the question. Okay. So whatever is provided in this part, I have used them. Okay. Right. So then the next one. For this, what are we going to do? For this, again, for centripetal force, we can use T, M is M, and for radius, we have to put L, the new length, into omega squared. So our purpose is finding omega this time. And for T, but again, T is equal, tension is equal to, we have found it using Hooke's law, K L minus L naught. Let's substitute that, L minus L naught, and that is equal to M L omega squared. If they ask you to find omega, what will you do? You will make omega square the subject, and that will be K L minus L naught divided by ML. So omega is going to be square root of K bracket L minus L naught divided by ML. Again, please don't try to by heart this. If you get a question, start from scratch, apply the equation, get this answer. Okay. Now this question was there in 2015 or 14. Wait a minute. It was there in one of the past papers. The past paper question is, yeah, the past paper, you can check it. It is from 2014. 2014. Right? 2014. So let's try that quickly. This question is quite similar to what we discussed earlier, 2014. There are only few differences, just some differences. Quickly, I'll explain this. What's going on, right? A light spiral spring has an unstretched length of length L. What is the meaning of that? That is the initial length of the spring. That is the initial length of the spring when there is no, what do you call that, extension. When there is no extension, there is this thing. So initial length is L. When there is no extension, the length unstretched. And spring constant K. Okay, K is the spring constant. No problem there. K is the spring constant. A small object of mass M, they have indicated that, is attached to one end of the spring, and the system is rotated about a vertical axis that passes through a small light ring attached to the other end of the spring as shown in the figure. So the point is, it is rotating. It is rotating like this now. If the object travels along a circular path of radius of capital R with constant angular speed omega, keeping the spring on a horizontal plane, okay, so horizontal circular motion, then we are supposed to find the equation for omega. Right. Now omega is there, ready. Then we need to find out the force acting on the spring, and that is obviously going to be the tension. There's going to be a tension acting on the spring like this. And it's a spring, so we can apply Hooke's law. And for what is the extension this time? What is going to be the extension this time? What is going to be the extension this time? The stretched spring is R in length and unstretched spring is L in length. Therefore, the extension, the additional length or the increase in length is going to be R minus L. That is going to be the extension of the spring, R minus L. So if you apply Hooke's law, F equals Kx to find out this tension, that is the force equal to K into, instead of X, you will substitute R minus L. Okay, now we have to find omega. We are almost there. What do you do to find omega? You use this equation. Centripetal force is equal to mr omega squared. And this capital R is one more thing in this question. That is the radius of the circular path as well. Radius of the path as well. Correct? Fine. Then let's substitute the values. Centripetal force here is tension. Mass is m. R is R itself. And omega we have to find out. I'll mark it as m omega squared. But we just found out capital T in terms of K, R and L, that is K, R minus L according to Hooke's law. So if you substitute that value here, K bracket R minus L, that is equal to M R omega squared. Therefore, omega squared will be given by K R minus L divided by MR. And that will finally give us an answer. Omega is equal to square root of K R minus L divided by MR. Simple M. Okay, simple M is the only mass here. It's more or less the same thing. Earlier, I think we discussed with L and L naught. Instead of L, they have used R here. Instead of L naught, they have used L here. That's it. So I think the answer is, yeah, obvious. It's the first one, is it? Or second one? No, first one. First one. It has to be the first one. A toy car connected to a fixed point by an elastic string, as shown in the figure, travels in a horizontal circle of radius 2r. The initial unstretched length of the elastic string is r. Now, this is a key point. The initial unstretched length of the string, elastic string. Now, this is not a spring. This is a string. It's r. Now, the period of rotation is of the car is capital T. Now, this T is not tension. Careful, huh? This T is not tension. It is the period of rotation. The car is then speeded up until it is moving in a circle of radius 3r. So there are two different circular motions. Okay, right. I'll draw a diagram. Let's see. If the string obeys Hooke's law and resistive force is negligible, the new period of rotation on the car will be. Now, capital T, people, it's not tension anymore in this question. It is the period of rotation. So you have to approach it in that way. Let me start. Now, first and foremost, when the object is connected to the string, when it is unstretched, the length is L. The length of the string is R. Sorry, the length of the string is R. So let's say simple R. Okay, and here tension is equal to 0. Tension 0, extension is also 0. Both are 0. Okay, right. Now, first circular motion. Let's move to the first circular motion. What is happening there? The object, when it's performing circular motion, the string is stretched to a length of 2r. So let's take the mass is m, and yeah, it's performing circular motion. Right. So let's see. Right, it's performing a circular motion like this, and it goes on like this, right? Fine. And the omega, I'll take the omega as omega 1 here, but the problem is they are talking in terms of period of rotation. So omega 1 and t1. T1 is our capital T. T1 is period of rotation, capital T. Okay, and radius now the new length is 2r. So for this circular motion, guys, there will be a tension acting. I'll take tension as F now, without making it complicated by putting T. F1 is the tension. F1 is the tension, and 2r is going to be our radius. 2r is our radius. Okay. Now, what is going to be the extension for this case? Arya, what is the extension on the string? What is the extension on the string now? That is going to be r, because the initial length was simple r. Now the new length is 2r. That means the string has extended by an additional length of r, simple r. Let's apply Hooke's law. F equals kx. F is f1. K is k. I think that will get cancelled off when you divide. X is the extension. So instead of extension, you have to put r. So f1 is equal to kr. And next, what do you do? You go for the equation. F centripetal force equation is equal to mr omega squared. Right. Now, what is the centripetal force? That is F1. Mass is m into radius is 2r into omega squared. Now, omega squared is actually, okay, omega 1 squared. Never mind. We'll draw it like that. F1 is kr. How did kr come? K is the spring constant. Simple r is the extension. Initially, it was r. Now, it is 2r. Equal to m into 2r into, the question is about period of rotation. So what I'm going to do is I'm going to convert omega to t. We have learned omega can also be written as 2 pi over capital T. Angular velocity is equal to 2 pi divided by period of rotation. Therefore, for omega 1 squared, I can put 4 pi squared over t squared. Right. So what is our plan then? Shall I leave it? Okay, I'll make t square the subject. If I make t square the subject, I know this is a bit complicated, but bear with me. You will be getting 8 mr pi squared. 8 mr pi squared. Okay, wait. Before that, we can cancel out the things. It's better to cancel out the things we can cancel out, right? It's cancelled. And what else do we have? That's it. So moving on. T squared, that gives us t squared is equal to what? 8m pi squared divided by k. First equation. It's not that hard. It's just you have to do each step carefully. That's all. Substitute the values carefully, and that's it. Basics. And this is the first circular motion. In the second circular motion, what's happening? The car is then speed up until it is moving in a circle of radius 3r. Now they have changed the radius. Radius is increased to 3r. So let's draw a larger circle now. Right. Radius is how much now? 3r. So mass m is here rotating, and the radius now, people, it's 3r. So the circle has become bigger. Just drawing a circle for the sake of drawing. Right. Okay, come on. Right. This is a circle. And now there will be a new omega, no? New omega. I'll take it as omega 2, and there will be a new period of rotation corresponding to that, T2. T2 is what we are supposed to find out. Okay. Right. And the radius now, this 3r is the radius, and the new tension acting on this, will take it as F2, the new tension. Right. So let's repeat the same steps very quickly. What is the extension now on the string? Extension, its initial length is r, initial length, first length, and it has become 3r. That means total of 2r has increased. 2r has increased. Right. And then we can apply the Hooke's law. F equals kx. So F2 this time, it's going to be equal to k into 2r. Therefore, F2 is equal to 2kr. Done and dusted. And then again, let's go to centripetal force equation. That is mr omega squared. For centripetal force, I can substitute F2, m into r now, it's 3r into omega 2 squared. Instead of omega 2 squared, I will directly substitute the value. That is 4 pi squared over T2 squared. Hope you all can agree with me on that. Why is that, people? Omega 2 has to be equal to 2 pi divided by T2. I substitute directly without wasting time. And then F2, what is F2? If not, okay, wait, I'll put it as omega 2. Sorry. I'll put it as omega 2 squared, and let's go to the next step. You can reduce the steps. I'm just writing these steps to step for you to get a better understanding. F2 is this 2kr. 2kr is equal to m into 3r into omega 2 square is actually 4 pi squared over t2 square. Right. Then what are the things we can cancel out quickly? I think r and r can be cancelled out. Yes. And this 2 and this 4 can be cancelled out. I'll get a 2 here. And finally, you will end up in an equation like this. If you make t2 the subject, t2 squared, guys, it's going to be equal to what? 6 m pi squared divided by k. 3 into 2 is 6. M and pi square are there. Okay. T2 squared goes up, k comes down. Equation number 2. Almost there. We are almost there. What should I do? I should find an equation for T2, that is the new period of rotation in terms of T. So let's divide the second one by first one. If you divide the second equation by first equation, what will you be getting on the left hand side? T2 squared over T1 squared equals, divide this by this. Okay, divide this by this. What is the only thing which is going to be remaining, people? M pi squared will get cancelled off. K and K will get cancelled off. It is 6 over 8. I can put it as a 3 over 4, is it? 6 over 8 is 3 over 4. And then I think we need to, the T1 squared thing, I think it should be T squared here. Sorry, it should be T squared. Because initial one is T, it's given, right? And then let's make T2 square the subject. T2 square is equal to 3 by 4 T squared. Therefore, the final answer for T2 will be given by T2 is equal to, if you take root, you have to take root on either side. Square root of 3 is root 3. Square root of 4 is 2. Square root of T square is T. Therefore, which one looks like this answer? Fourth one. Fourth one is the correct answer. Not the first one, sorry. Someone had said first one is the answer, but it's not the first. It's really the fourth one. Okay, right. It's just, in the previous question, we did one step. Here, we have to repeat the exact step one more time. That's all. It might be a little bit time consuming, but it is not impossible at all. Quite doable, this question. It's just you need to have a focus and you need to pay attention to minor details. Now the next question. It is the next case under strings. This is called a conical pendulum. A conical pendulum. An object connected to a string, and the string is rotating like this. So pendulum means a string doing this is what you call pendulum. It will be like this, and it will go here, it will go here. That's the normal pendulum in one plane. But if it is now happening along a cone-like shape, that's why we call it a conical pendulum. Right. Now, how many forces will be acting on this object? One will be the weight, like we have already discussed this several times. Weight will be acting downwards. I'll mark it as mg. And there will be, okay, if this is theta, you can take the alternate angle. Alternate angle is also going to be theta. This is theta. Fine. And okay, very important, tension is going to be acting like this, tension. But we can't use T directly. We rather have to take the components of T. So there will be a vertical component of T, that is T cos theta, and there will be a horizontal component of T towards the center, that is actually T sin theta. And not only that, there is one more thing we need to be mindful about. I will draw the diagram again separately. The radius of this circular part, the radius of the circular part. What is that going to be? Right. There is like if you take a plane from horizontal, vertical plane, this length is L now because it's slanted, and this length is theta. And if this is L and this is theta, this length is going to be L cos theta. Whereas this length is going to be L sin theta. This length is going to be L sin theta. So, who is the radius? Who is the radius for this circular part? That is this length, and that length is in fact L sin theta. Okay, you can't take L directly as the radius. We have to be mindful about that. Careful, okay? Right. Now, what is the question about? if the air resistance is negligible, the velocity of the particle, by velocity they mean v. If it is omega, they would have specifically mentioned angular velocity, right? So always we know that when an object is performing circular motion, it will have omega and it will have a speed, I mean the tangential speed as well, v and omega. Now let's find both v and omega. It's not a big deal. Let's quickly find both. But before that, whenever there is a string which is slanted like this to the with the vertical, you have to consider the components. Now, one component is going to be our centripetal force. T sine theta is going to be our centripetal force, and the object is performing a horizontal circular motion. Therefore, the vertical resultant force must be 0. So, upward force must be equal to downward force. Therefore, upward force is T cos theta. T is something we introduced in addition, mg. Therefore, for T, downward force is mg. Upward force is T cos theta, downward force is mg. Therefore, T is actually equal to mg divided by cos theta. So, you need to do all these things and get ready for the equation. So, what is the equation? First of all, let me start with this. Centripetal force is equal to mv squared over r. I'm going to find the actual answer we are supposed to find. Centripetal force T sine theta. Careful. M into v squared, we had to find it, divided by r, that is L sine theta. Look at the answer. T is not there in the answer, no? Because T is something we introduced. M is also not there in the answer. Why is that? Because for T we know, but T is equal to mg divided by cos theta. Therefore, let's substitute that value. So mg divided by cos theta into sine theta, that is equal to mv squared over L sine theta. So if you have a close look at it, m and m can be cancelled out. All right. So I will continue it here. What else can I do? This sine theta divided by cos theta. What is that? G sine theta divided by cos theta. That is tan theta, isn't it? So you can write it as G tan theta on the left hand side. On the right hand side, I have v squared divided by L sine theta. I need to find v, so I'll make that the subject. V squared is equal to Lg sine theta tan theta. Okay, L sine theta goes up, you'll get this. So v is actually equal to square root of square root of Lg sine theta tan theta. They're asking for velocity, that is v, that is this. First one is going to be the answer. Okay, right. In case if they had asked you to find omega, what will be your approach? Simple. You will use the other equation, FCP equal mr omega square. Let's say they have asked to find out angular velocity, then you have to start here. Don't need to do this. Centripetal force is T sine theta equal to m into r. R is the radius, that is L sine theta into omega square. Okay, right. This time sine theta will get cancelled off. See, sine theta gone. Right. And again, let's substitute the value for t. Now we have figured out t is actually equal to mg divided by cos theta. Correct? So if you substitute that, mg over cos theta on the left hand side, that is equal to ml. Sorry, m is okay, ml omega square. M is not cancelled out yet. Now you can cancel out m. And then let's finish it off. Omega squared, people, that is going to be equal to g divided by L cos theta. Omega is actually equal to square root of g divided by L cos theta. That's all. Done and dusted. But this is not what they are expecting you to get. And even if you find omega, this answer is missing, na, everyone. So that reconfirms that they are asking for the tangential velocity. Okay, so the answer for this is first, but in case if they ask omega, you will have to approach in this method. Now, the next case we are going to discuss is completely different one. That is the vertical circular motion of an object connected to vertical circular motion. There can be different types of vertical circular motions. Where you connect an object and then you rotate it vertically. So it will rotate. Like in Parahara and all, they rotate it vertically. Something like that. If not, you connect a stone to a rope and you rotate it vertically. like a vertical circle. Okay, so when something is moving vertically, weight also it's going to play a major role. There are few examples of vertical circular motions. One is this, like I was saying all this time, an object connected to a string and rotated vertically, like this. Yeah, that's the first thing, because it's better if you know a few examples. Example one, an object connected to a string which is rotating vertical. Now let's quickly analyze certain things here. It's a very important case. If you get a question, then you have to be ready. Mostly in model papers, they might ask, in your term test papers and all, you might come across questions like this. So I'll consider different situations of the object. The string can be in different places like this when the object rotates. Right. Now my question is, will the object rotate at same speed? Can the object rotate at the same velocity? Yes or no? Can the object rotate at same velocity? And then I will take a random position of the string somewhere here and also somewhere here. Let's extend the same two positions, right? With the angle also, let's try. With the angle, right? Fine. So will the object rotate at same speed? No, the object is not going to rotate at same speed. You know the reason? The energy is changing, people. Kinetic energy. So I mean, potential energy keeps changing. When the object rotates vertically, high potential energy, low kinetic energy, low potential energy, high kinetic energy. So the speed can't be same. Speed will keep varying. Now the object is here initially. The object is here. Then the object is here. Then the object is here. And the object is here. Likewise, the object is at different places. Now we all know when the object performs circular motion, we can mark something called tangential velocity. So let me mark the tangential velocities of the object. At this point, it will be like in this direction. Okay. At this point, it will be vertically downwards actually. Wait, no. Tangential velocity, I'll mark it little outside this object like this. Tangential velocity. If not, it will be confusing because I had to mark the forces as well, right? So tangential velocity like this. Never mind. Okay. Here it's like this now. And here it's like this, and here it's like this. So what I have marked are the tangential velocities: v1, v2, v3, v4, v5, v6. Now our purpose is going to be finding equations for these. Okay, right. How many forces are acting on the object here? How many forces? How many forces will be acting on the object here? There will be two forces, people. One is mg plus T1. Tension will be towards the center. This is the center and tension will be towards the center. Two forces. And yeah. And here mg, that is downwards, no problem with that. And tension will be acting towards the center. T2. And here I will take this angle as theta. Okay. This angle is theta. That means this angle is also theta, vertically opposite angle. There will be mg acting downwards like this. And there will be a tension acting towards the center, T3, like this. Wait a minute. Yeah, okay, T3. Never mind. Yeah. And here, careful, mg will be downwards. Mg and tension will be upwards towards the center, T4. And this one, again, tension will be towards the center. I'll take it as T5 and weight will be downwards mg. And here, again, without wasting time, quickly mark mg and tension towards the center, T6. And if this is theta, this is also going to be theta. All right. And if this is theta, this is going to be theta. I will need this angle. Now, this is theta, is this vertical line, the same line. This small angle is also going to be theta. Okay. Right. Ready. Positions. Let's mark these positions. This is position 1, position 2, position 3, position 4, position 5, and position 6. Now, what I'm going to do, guys, is simple. I'm going to apply the equation for each position. That's what I'm going to do. So let's start. The main equation is centripetal force equals, I'll do it here. Main equation is centripetal force equals mv squared divided by r. I forgot one thing. Let's take the length of the string as L. Length of string is L. Length of string is equal to L, and it's an inextensible string. So radius of the vertical circular path is L. First point, what should be the equation? First point, centripetal force is mg plus p1 equals mv1 squared over L. You need to put whatever the velocity speed there, and you need to put the resultant force towards the center. That is the equation. And in the second one, what is the centripetal force, people? In the second one, now the string is horizontal. Therefore, centripetal force must be horizontal. So only T2. T2 equals mv2 square over L. Right. So can you help me with the third one? What should be the centripetal force? Third one, hurry up. Can I get some answer from you all for the third one? What is the centripetal force? I think we discussed about this in the middle as well. Go ahead. What will be the centripetal force for this point, people? Yeah, good. This tension is, I have marked it as T3. T3 is there. Don't forget, T3 is there towards center. And mg cos theta is away from the center. Therefore, you have to subtract that as well. Mg cos theta, and that is equal to mv3 squared divided by 2. Okay? Not divided by 2, divided by L. Sorry. Fine. Fourth one. Tell me the centripetal force. Fourth one. When the object is here. What is centripetal force? Arya? For fourth one, what is centripetal force? Yeah. T4 minus mg. T4 is towards the center, mg is away from the center. So it's T4 minus mg, and that is equal to mv4 squared by L. mv4 squared by L. And at position 5, what is centripetal force at position 5? It's just T5 because it is towards the center equals mv5 squared over L. Probably T2 and T5 must be same because they are at the same elevation, though they will have the same speed. Yeah, same. Only the directions will be different. And last but not least, sixth one. Can you tell me the centripetal force for sixth one? Good, good. That should be T6 plus mg cos theta, because mg cos theta is going to be towards the center. T6 is also towards the center. Both must be added. mv6 squared over L. Good. Now, the reason for writing all these things, they will ask you one of these positions, or might be two. So if you know all these things, then whatever the question they give, you are ready. Then you can do it. Okay. Right. So that's the first example I wanted to share with you all. And second example, or something we discussed earlier, second example, a bike stuntman riding his bike on a vertical circular path. Vertical circular path. Okay, so there I think we discussed that. I'm not going to analyze that like this. It's this more or less same. Only difference is here we have T tension. There we will have R. That is the only difference. That is the only difference. So there's no point of analyzing this one by one there. Okay, right. Now then, why did I specifically mention this? If it is the same, now it's like this, right? Like this, the object will be rotating like this. Now, where at which point is the object faces, or the stuntman faces the highest risk? At which point? At which point of his motion is he facing the highest risk? Where? Obviously here, top. Imagine if he falls down, finished. He will land on his head. His neck will break. He'll probably die. So we don't want that to happen, right? Now think carefully and tell me, should he go fast or slow? What is going to save him? Moving faster or going slower? What will save him? Just think practically and tell me. Yeah, very good. Obviously, he has to go faster. He has to go faster, because if he goes faster, then only he can maintain the contact between the surface. and his tires. Okay, so there was a model paper question. That the question was this: let's say the radius of this path is given as simple r to you. The radius of this vertical circular path is given as simple r to you. Sorry. So this was a question. What is, and mass of the bike, let's take it as simple m. What is the minimum velocity? What is the minimum velocity the biker should have to ensure his safety? Ensure his safety. Ensure his safety. Okay. That was the question given. So the answer can have R, G, M, all those things in the answer. Sometimes M might not even come. So what is the approach for this question? How should we approach this? Right now, they are asking for the minimum speed. So imagine now here is the question, most critical question. This is the most critical position. Therefore, you have to analyze the most critical position. Okay. Now, when he goes at the minimum speed, what is going to happen? When he's now going at the minimum speed, he's going at the minimum speed. So what should I do now? When he goes at the minimum speed, there will be only one force acting on him. What is that force? Only his weight. R will be there, but when his velocity is minimum, that is when R becomes 0. Can you remember we did questions like this under moment? At the verge of toppling questions, hope you all can remember. So when you have two supports like this, and when a person goes here, people, and when the plank is at the verge of toppling, what will we do here? We put R equals 0, correct? So here you have to consider the same way. Only W will be acting. R at this point is 0. R will be 0. I'll mark it here. There R 0 at maximum height. Maximum height when velocity is minimum. When velocity is minimum, since what bike will be at the verge of losing contact. Bike will be at the verge of losing contact. That is how you have to do this question. Because if you put an R value, then you can't definitely find one. So you have to put R as 0. Okay. Now at the maximum height, what is the equation? At maximum height, what is centripetal force? Tell me. Hurry up. Maximum height. We need to use this equation. Huh? Centripetal force is equal to mv squared over r. Can you all tell me what is the centripetal force? That will be mg. That's all. Nothing else. Mg. Normally we put mg plus r for normal situations. Here we put mg plus t, but here we are going for a minimum situation. Therefore, we have to put only mg. Instead of w, I'll put mg. Yeah? Right. Mg equals mv minimum squared divided by r. So what can we do? M and M cancels off, like I told before. GR goes up. Therefore, I'm getting an answer like this. What is the answer? Wait. V minimum square, that is equal to GR. Therefore, finally, V minimum, that is equal to square root of GR. Square root of GR. Okay, please don't by heart this. There's no point of by hearting these equations. Start from the scratch. If you want to by heart something, by heart this. That's enough. Mark the forces correctly, analyze the question properly, mark the forces correctly, then apply the equation. That's it. Right. So this is a model paper question. It will be RGR. Right. Fine. And sometimes they will ask you to find this velocity here. Then you will put an R, mg, and then you will find it like this, like T4, like this. That's easy. R minus mg is equal to mv squared over R, simple R. And that's a different story, but situation like this is how you have to handle it. The next example under vertical circular motion is a swing. Now, what is a swing, people? Swing means it's like this. A chain or a rope will be fixed to one point, and that will do this. It will actually swing. So, yeah, it will take a circular path like this. It's not a complete circular path. That is the important thing we have to understand. It's not a complete circular path. It rather takes a path like this. So, imagine a child swinging like this. Right. So initially the object will be here, then it will be here, then it will be here. So it goes on like this. This is a swing. Huh? So back and forth, it's going to go up and down like that. Right. Fine. Now here things are a little different. What is the speed here at this point? What is the speed? Hurry up. What will be the speed here, people? What will be the speed at the right extreme corner, left extreme corner? What will be the speed? What will be the speed? Haven't you used the swing? Raise your hands if you have played on a swing. What will be the speed? 0. Momentarily, you will go stop and come back. It's not like you're going to stop there forever. For a millisecond, you will stop there and then come back. Hope you have observed that. Right? For a moment, you will stop there and come back. So it's like object going up, coming down. We're talking about a swing. Okay, so when you swing, you go like this. It's a periodic motion. And when you're here, you stop for a moment. And then when you go here, you stop for a moment. And what about the center part then, people? What about the center part? What will the object do? It will be moving at its maximum speed, either to the right or to the left. The speed will be maximum. Hope you can understand that. Okay, speed will be, if in the corners, if the speed is 0, definitely in the middle, speed will be maximum. Next time when you swing, see if you can feel this. When you come to the lowest point in your trajectory, you will feel the maximum speed. Okay, and the highest points, you will feel the velocity to be 0. Right. Now, how many forces are acting? Let's take the length of the spring, so the swing. Let's take this length as L or something. Trying to apply an equation here. So I'll take the length of this is this as L. Dot length is L. Okay, L. Right, L. And yeah, this angle we'll take it as theta. Right. And at this point, we know it's moving either to the left or right at maximum velocity. And at that point, we know the tensions acting. Tensions, right. So there will be a tension here. I'll take it as T1 or T. It's going to be actually T max, maximum tension. T max, and here it's going to be mg downwards because maximum tension because of velocity maximum. Okay. Now for this point, when you apply the equation, FCP equals mv squared over r. What is FCP, guys? Maximum tension minus mg equals mv max squared divided by, instead of r, we can put L. Therefore, maximum tension acting on the string is equal to mg plus mv max squared divided by L. No need to by heart this. Just like I said before, this is how you apply the equation. Okay, right. What about this point then? When the object is swinging like this, definitely there will be a tension here. It will be taut. So I'll mark that tension as T, and there will be mg acting here. Mg. And if this is theta, we know, we have discussed it before as well. This is also theta. Now, how do you find theta, T this time? How do you find T this time? Can an object be at rest like this with just two forces acting? They are not acting the same line. No. But the thing is, it's not at rest. It's a momentary rest. So if you apply the centripetal force equation for this part, see if you can understand. Centripetal force equation is equal to mv squared over r. Guys, what is the centripetal force here? It is going to be T minus mg cos theta. Hope you can agree with me on that. It's T minus mg cos theta equal to velocity is 0, no? So it's going to be m into 0 squared over L. Therefore, this side becomes 0. So T is equal to mg cos theta. We can say it this way. Where is that? The tension at the highest point of the trajectory. Tension at the highest point of the trajectory. And tension at the lowest point of the trajectory, you can find it this way. This is okay, not very hard. I mean, you know this. I don't have to work because we already discussed that vertical circular motion. So swing is a part of that vertical circular motion. Fine. Not even half. If it is half, then imagine you're going here. Okay, that's super dangerous. Good. So we are done with this, and let's quickly try a past paper question to wrap this up. Right. So the swing question from a past paper book comes from 2001. A child of mass 20 kg is sitting on a swing of negligible mass. So swing has negligible mass. The swing is attached to its pivot by 2 ropes. So this is a little, we have to be little careful. It is connected to 2 ropes like this now. So 2 ropes are providing the tension, right? And the swing is going to look like this. Here the swing is going to look like, and the swing is going to swing actually like this. It's going to swing. I'm not going to draw the path. And like I said earlier, when the swing is here and here, the velocities will be 0. But I don't think they are worrying about those 2 points. Let's see. Each of length 3m, therefore the length is 3m. The length is 3m means the radius is 3m, isn't it? The radius is going to be 3m this time. Radius 3m, but remember 3 meters. There'll be tensions like on this as well as this, and then there'll be, I have not drawn the child, including the child. Now there will be weight. Weight is equal to mg, and what is the mg? 20 kilograms, so it's 200 Newton. The maximum speed of the child during a swing is found to be 3 meters per second. Maximum speed is 3 means at this point. Child might be going to the right or going to the left, doesn't matter. Speed, the value only matters. Maximum speed. Okay, maximum speed will be at the bottommost point. Why at the bottommost point? At the bottommost point, the gravitational potential energy is minimum. So 0, kinetic energy will be maximum. That's why it's maximum. So what are they asking? Maximum tension in each rope. So the tension will act in each rope. Then you have to apply the equation. Right. So what is the plan here? Let's go with the same equation. Centripetal force equal to mv squared over r. Now for centripetal force, I have to put 2t minus mg. Read the question carefully. Maximum tension in each rope. So t is what they're asking us to find out. 2t minus mg equals v squared over r. Never mind. Let's substitute the values now. 2t minus mg is 200 equals m is 20 into v squared is 3 squared divided by r, 3 meters. Okay. Then you can cancel out the 3 with the 9. Then you get 60 there. 200 comes to the other side. Then what do you get? 2t is equal to 260. 2t is equal to 260. So if you choose 260, it's wrong. The answer is over there. So T is equal to half of that, 130 Newton, because tension in each rope is what we are supposed to find out. First one is the answer. So careful, 260. Most of you might have come up to here, but unfortunately that is not the correct answer. If you have come up to here, you have done almost all the work, 99%, okay. But unfortunately, it's the tension in each rope, so you have to carefully find. So when you do physics MCQs, there's a technique you need to use, people. Always mark that unknown, T, X, L, M, whatever it is, for the exact thing you need to find out. So here I have marked T, the tension in each row. So if you find T, you have the final answer. So try to find T. That's what you have to do. Okay. Right. So answer should be first step.